Hello, everyone. Welcome to the second day of the Global Brain Consortium. In this room, we are going to talk about the nonlinear brain, and the head panel is Pedro Valdez Sosa.
So basically, this is our session today. You can see it. But before diving into it, I would like to express that this is a session that's very close to my heart. It's very brief, and I'll explain why. I got involved in nonlinear dynamics of the brain around the year 89, and I spent a lot of time at the Institute of Statistical Mathematics in Tokyo. One of the books I saw there, and I haven't been able to find it again, said about nonlinearity, and it's this thing here. There's the science of linear systems and the non-science of nonlinear systems. And this expression was because what they said at the time is that it was so complex or so diverse, nonlinearity, that it wasn't a science yet. I think that things have advanced considerably, and I think that we're going to be seeing just some facets of that now. And let me touch briefly to explain the connection between the talks. First, I'd like to mention work that was started by Roberto Pascual, and then a few years later, we did this, which is to try to decompose the spectrum into components. This is the C-alpha model. There's let's say, a different variant called FOOF that's been very popular, but this is an old idea from '88, and then we followed this up multivariately here. This decomposition is a data-driven decomposition. A bit later, we started fitting statistical models to the EEG using narrow mass models. So we turned the integral differential equations into stochastic differential equations and used Osaki's linear linearization method to fit EEG to data. Now, this line of work was then followed years later by this paper, which is from 2009, which then extended this to have delays between narrow masses and large scale. Here you see the delays. This is the equation. This is how we calculated delays. We calculate them realistically using diffusion-weighted imaging to get an idea of the path between two narrow masses. And then we have here the paper, which did one of the first large-scale simulations of EEG and fMRI. This work has as a complement not the description either of the EEG spectrum itself or a narrow mass model, but also that when we have a spectrum, we have cross spectrum, it lives in a nonlinear space. And this is from the work of Ming Li, which was published recently, and it's based on a concept which is that when you look at the manifold of the parameters, they're not in a linear space. And you can't use Euclidean multivariate statistics, but rather statistics that's based on curved spaces. This has been not only used to describe the spectrum and get good discrimination, but it's also been used to study mediation. That is to say, to fit as an object cross-spectral matrices to do mediation. So then I can explain how the session goes together. First, I have to say that the first presentation will be by Ludovico Minati. Ludovico is a really unique guy. He's one of the few people that I know that can either publish the way we publish on differential equations, or even more interesting, construct physical models of the nervous system. He is very active, and in fact, there's already interactions with one of the presenters here, Regal, who you will see. And what I can say, he's very prolific. And so it's very good to start out, because all of nonlinear science started with circuits, and then it got lost. You know, it was just equations. So to start out with Ludovico is a very good idea. Now then, we have the presentation for spectral analysis and composition of Qian Hu, who will do a linear decomposition. Ying Wang will extend this to nonlinear harmonic models of the spectrum and bispectrum, and then going to narrow mass models. And his lady will build on the prior work of the group and extend it really in new directions. Carlos will use Riemannian geometry to study mediation, and then Ronaldo will end by showing us how, if we're going to do regression equations to describe, let's say, the dependency on age of any parameters that live in a Riemannian space, you have to use special methods. So this is the overview, and now I'm very pleased to be able to present my colleague and friend, Ludovico. So it's your turn, Ludovico. I'm going to stop sharing.
Thank you, dear Pedro, for the wonderful introduction, setting expectations that are certainly way too high for me, but nevertheless, thank you. I particularly appreciated your comment about the fact that the study of nonlinear systems started with physical objects, particularly with circuits and not only, and then became more and more theoretical, but it developed a sort of disconnect between this ever-growing literature on numerical systems and a more physical investigation. Now, I am an experimentalist mainly. I was born with a screwdriver, or rather with a soldering iron in my hand, and that is the perspective from which I will give this talk today. So, thank you very much again for the invitation. I will present a very brief survey. It's just an overview, and I hope you will excuse me for that, of the topics on which I've been working for the last 10 years, more or less. The underlying idea is to establish, in an explicit and experimental way, commonalities between the dynamics of neurophysiological phenomena, as we observe them biologically at the micro, meso, and macro scales, and, on the other hand, the behaviors of rather inconspicuous, rather small, as we will see, analog electronic circuits and systems. And the rationale for doing this will hopefully come clear in the next few slides. The underlying idea is that many of the dynamical phenomena that we observe neurophysiologically are actually reflections of universal nonlinear phenomena. And as such, these can be captured also in very different systems that are potentially much simpler, much easier to manipulate, and also potentially to apply from an engineering perspective. And this gives a clear difference and complementarity with respect to the approach of neuromorphic systems. So first of all, I will talk about signal generation, and I will focus on chaotic time series. Actually, today I will not at all discuss their properties in a mathematical sense. Rather, I will consider chaotic oscillations in this context as a paradigm to obtain signals that are fully deterministic, yet very rich, very qualitatively diverse in their features, and originating from generators that are rather elementary in circuit terms. So let's start. This is where it all began for me. It is the first circuit that I worked on in 2014. It is extremely simple, as it involves just one transistor, two inductors, one capacitor, and one variable resistor. The technology obviously is more than 50 years old. However, this is absolutely not a usual oscillator, because as we tune the resistor or the applied voltage or both, what is observed is not just a change in frequency or amplitude of a periodic oscillation, as is more common and rather trivial. Instead, much more interestingly, what we have are phase transitions between different dynamical behaviors, as shown below in the bifurcation map and in the spectrum. Some of these behaviors, not all, but at least some of them, are quite reminiscent of neural recordings, such as the generation of volleys of voltage fluctuations that are shown here, that loosely recall post-synaptic potentials. Now, the key message is that this transistor operates in a strongly nonlinear region, and suitable resonance and feedback are provided over multiple frequency ranges by means of the external components. Clearly, there is not any attempt to be realistic in terms of physiological variables or morphology or structure here. Nevertheless, one can start to see some phenomenological commonalities. Then it is possible to generalize this circuit idea and create an entire family of circuits by describing their topologies and component values as chromosomes, basically a bit string, and applying a genetic algorithm, a random search, or something similar under suitable heuristics. As we can see here, totally new atypical circuit topologies are observed. These have become known as the Minati-Frasca circuits or oscillators. The one at the top is perhaps the simplest chaotic circuit of this kind ever discovered and generates a funnel-like attractor. More interestingly, for today's purpose, the one below is slightly more complex as it includes two transistors, but it generates a spike train, also including bursting, which is in many aspects reminiscent of actual potential recordings, as we will see more extensively later on. Now, these objects tend to be quite low-dimensional in their dynamics, and this is an important difference with respect to neural dynamics. One way to render the dynamics of these oscillators much higher dimensional is to introduce fractal resonators made with capacitors and inductors in a fractal arrangement, mimicking the effect of the compartmentalization in dendritic trees. Fractal dimensions of the dynamics exceeding 6 and even approaching 8, indicative of high-dimensional chaos, could be readily obtained, while retaining just a single transistor as the only active component. And this, I think, is a rather unique result. Now, one challenge is realizing such oscillators on an integrated circuit, which is necessary for engineering applications and also for constructing larger networks. Here you see an idea of how to realize the same concepts using CMOS technology based on 3 inverter rings having lengths 3, 5, and 7, basically the smallest odd prime numbers, cross-coupled between themselves and individually current starved. Besides generating oscillating signals, which can be periodic or chaotic at frequencies from few hertz to few gigahertz, what is more interesting today is that for suitable settings, one can again get spiking-like activity, as shown in the graph above, even with some evidence of power law scaling, or on the other hand, as shown below, the generation of 1 over F type noise. So even from such a simple circuit, potentially there is an incredible amount of versatility to generate signals that we are used to observe neurophysiologically at different scales. Now here's quite another experiment where a 2-dimensional lattice was realized using gas discharge tubes, capacitors for couplings, and resistors to a globally applied voltage. Once again, very old technology, but that is actually something that I am, in a sense, proud of, that we can still get new results without needing very complex implementations all the time. As you can see above, as a function of the globally applied voltage to this lattice, there is a clear first-order phase transition between a low-rate low-order phase and a high-rate high-order phase, while the latter is reminiscent of a self-sustained epileptic discharge. Quite obviously, there is a strong hysteresis, so there is a first-order phase transition. However, at the interface between these two phases, one observes critical avalanching, with the same scaling exponents for size and lifetime of the avalanches that are observed in the neural cultures. Actually, there is again nothing mysterious, there is nothing strange. It is just that they both belong to the same general class of branching processes. Actually, based on the coexistence of first and second order features in this physical model, a new model for a spiking neural network dynamics exhibiting both first and second order phenomena was later formulated. From an engineering viewpoint, it is important to realize ultra-low power systems, as we know. And here I will just briefly mention another approach to realizing chaotic dynamics of a very similar kind, but based in this case not on transistors, but on a nanomechanical device realized at an NTT in Japan. Finally, there's been much talking about membristors, almost as a sort of holy grail, for decades, but almost all work was done using numerical models or circuit emulators. In this work, for the very first time, I could show sustained chaotic dynamics in a real physical memristor device based on chalcogenide chemistry. This is a device which, by construction, has a non-volatile variable, often considered as a candidate to represent long-term synaptic dynamics. Excuse me. Then I will talk briefly about pattern generation. With this, I mean the formation of spatial and spatiotemporal patterns via synchronization phenomena, which arise when a suitable population of oscillators is brought to interact by means of structural couplings. And here we are talking of anything from 10 up to, let's say, 1,000 nodes. As we will see, also in this case, there are universal phenomena that can, at least phenomenologically, be replicated electronically in quite an easy manner. One particularly simple and compelling example is the formation of clusters or communities. This is what gives rise to the modularity of a network. Ring networks, in terms of structural couplings, represent an interesting substrate to study this phenomenon, because each node sees the same number of neighbors, and clusters can grow along the ring. As can be seen here, as a function of the coupling strength via a resistor, a ring of single transistor chaotic oscillators can give rise to complex, low-frequency oscillations that underline this community formation. As a function of the coupling strength, as is shown at the bottom, the size of the communities changes, starting from isolated node pairs all the way up to engulfing the entire network. This ability to seamlessly change the community sizes without altering the nodal dynamics is quite reminiscent of what we observe in the brain, for example, in dynamic resting state fMRI datasets. A more exotic phenomenon is that of remote synchronization, where two or more nodes become preferentially entrained, even though they are not directly connected to each other in a structural sense. This seems pervasive in the brain, and a simple example is the frontal node of the default mode network, which does not have an obvious anatomical underpinning with respect to the three posterior nodes. This phenomenon, even starting from a ring, can be elicited, as you can see here, and can lead to very complex synchronization patterns. The particular phenomenon shown here, which I cannot describe in detail for reasons of time, has a diffraction-like effect, leading to a non-monotonic influence of topological distance on the level of synchronization. Further analysis of the underlying phenomena revealed this to be a sort of hidden synchronization phenomenon caused by a rather complex interplay between modulation and interference across multiple frequency bands, not explicitly designed for, but purely emergent from the chaotic dynamics. Interestingly, perturbing such network using noise leads to several phenomena, including paradoxical enhancement of synchronization. In addition, and separately, the propagation of external pulses, such as sync pulses, is actually highly selective in these networks. So they propagate remotely their own intrinsic activity, but not these external perturbations. And this is again reminiscent of what can be seen in TMS EEG in the brain, particularly under normal conditions, as the synchronization relationship, the underlying synchronization manifold, tend to be very robust in rejecting disturbances from the outside and not propagating them. On another level, another interesting idea is that of looking at the self-similarity of a network in terms of the correlation between the strength of the edges and the strength of the sums of the triangles that overlie each edge. Basically, this is about squaring a matrix once or infinitely many times and looking at the correlation with the original one. Now, what we can see is that even though the system scale is very different, we observe quite similar phenomena at the macro level in the entire brain, on neural cultures, and at the micro level in rather small electronic networks. Another aspect is the relationship between the architecture of structural connections and the dynamics of individual nodes, for example, regarding the effect of node degree. Generally, high node degree promotes the transition to chaotic dynamics, and as shown here, this is very visible in star motifs and in scale-free networks made from them, for example, using low-dimensional nodal dynamics like Rössler and Saito systems. On the other hand, as shown at the top, when a stochastic component is present, for example, in the context of a leaky integrated fire model, high local connectivity, meaning high node degree, appears to promote the emergence of stronger deterministic activity in the form of low-frequency fluctuations. Jumping again to another topic, I am trying to give an overview of all the various things. One aspect that is particularly intriguing is the possibility of non-monotonic relationships between the strengths of structural couplings and the the resulting synchronization. This can be seen in several natural scenarios. For example, some disconnection lesions in the brain are well known to paradoxically enhance synchronization rather than decreasing. Now, this phenomenon too can be observed electronically, for example, in this simple hierarchical network of Stewart-Landau oscillators, whenever there is a competition between different levels of a network for synchronizing a particular node. An example is shown here, and the coupling strength leads to a transient loss of synchronization before eventually global synchronization is arrived. Lastly, just mentioning examples of these complex phenomena from very simple networks, the same setup can give rise to chimera states. These are symmetry breaking states where a network spontaneously partitions itself into subparts, having differentiated dynamics, such as standing waves, traveling waves, amplitude depth, and so on. And this can be seen very clearly in this very small ring network. In neuroscience, these phenomena are thought to be at play, but they are not really well understood. But there is a particularly beautiful example, which is the single hemisphere sleep in dolphins, that somehow seem able to generate this very macroscopic chimera state, partitioning their brain into two very different dynamical states. Lastly, I wish to talk about some potential applications. One aspect that is particularly interesting to me is the construction of toy models, physical toy models, for example, small-scale networks of 100 nodes or so that can summarize effects observed macroscopically in the brain. For example, one here has a network made of a large ring with 4 superimposed and interconnected hub regions. These regions generate a transition to low-frequency, large amplitude activity, shown highlighted in red, over a baseline of weak stochastic fluctuations that is very similar to what is seen when comparing hub regions of the cortex with less connected regions of the brain, looking at the corresponding resting state fMRI time series as shown below. Another vector of application of these circuits and networks is the generation of signals that are complex and relatively realistic in regards to neurophysiological recordings, but have a known ground truth in terms of the underlying connectivity. Using this approach, the recordings from the network in the previous case were used as a basis to develop a new synchronization measure called warped phase synchronization, which includes amplitude information when calculating the phase coherence, and as such, can much better detect the underlying structural couplings. Now, this measure, developed on the basis of this data, later applied to an EEG BCI dataset, could considerably improve the recognition of imaginary motor conditions. A further application is the generation of spatiotemporal patterns having prescribed features, for example, to control biologically inspired robots. An example can be seen here, developed using a hierarchical connectionistic approach to drive a 6-legged robot. One interesting aspect is that with this approach, one can generate not only the central pattern, but also the individual leg trajectories, with considerable versatility, for example, to replicate ant and cockroach-like postures on the basis of some control parameter settings. Quite remarkably, one observes the spontaneous emergence of phenomena such as the hysteresis between gates in gate transitions that are well known biologically, but were not explicitly designed for in this system. Just very briefly mentioning, one can also apply a converse approach and try to model how real biological organisms, such as humans, react to low-dimensional synthetic chaotic trajectories. Now, when all these ideas are combined, it is possible to develop quite complex real-time brain-computer interface systems, such as the one shown here, allowing the real-time EEG-based control of a 6-legged robot. On a very different level, Another interesting application of nonlinear electronic networks is trying to replicate, this time in an explicit and realistic way, the dynamics of totally different physical systems, such as photonics systems. What you see here is an example that turns out to be very challenging because there is a very large span of variables involved in terms of magnitude and time scales. For example, when there are electronic and thermal phenomena interacting with each other. Nevertheless, it is possible to generate these analog electronic emulators. And what you see here is very similar properties between a photonic device, its numerical simulation, and the corresponding purely electronic emulator. Now, before finishing, returning briefly to the single transistor electronic circuits that I've shown previously, another interesting application is in distributed sensing. The underlying idea is to create a many-to-many network via wireless couplings, for example, through one inductor of the circuit. The resulting interactions can be used to reach a consensus such that from the statistical properties of the ensemble activity, one can estimate the statistical properties of the variable to be sensed. For example, the series resistor or supply voltage may be used as a variable to couple to a transducer, and the mean and the standard deviation can be calculated. What you see here is an early experiment on the lab bench involving a 4x4 matrix of sensor nodes that were powered by and sensed the light intensity while interacting with a globally applied exciter field. Now, along these lines, just briefly, two practical issues are the antenna size.
Sorry, Professor?
Yes. Yes.
You are running out of time.
Oh, I am very sorry. Okay, so I'm going to present this final slide only, and then I will close. So the one application which I think is quite interesting in this context is physical reservoir computing. So we heard a lot about reservoir computing in AI, but this can be done also with physical systems. And one can see here a network of these spiking oscillators that generates rather non-trivial synchronization patterns. And when the couplings are used to encode an input vector and the synchronization is used to encode the output, one can generate a highly effective reservoir. Last but not least, there is a lot of geometric beauty in the dynamics of these systems. So thank you very much for your attention. I do apologize for running slightly over time, and I hope that we can collaborate and expand this line of research together. Thank you.
Hello, everyone. My name is Xian Hu from Anhui University. Firstly, I want to thank Petra's invitation. It's my honor to be here, present our work. This work is to develop a model for EEG-MEG power spectral decomposition. This work can be dated back to 4 years ago. At that time, Brady Wojtek's group pre-printed the paper. It's called FOF. And we found the FOF is a typical parametric model, and using the 1/, power law function to fit the aperiodic component of the spectrum, and also using the Gaussian function to fit the peaks. And also they fit the spectra in the log scale. And we checked the different power spectra from the scope EEG and also the intracranial EEG, especially for the intracranial EEG. This figure is the plot after doing the clustering analysis of the power spectra in the precentral gyrus. And you can see here the different electrodes in the precentral gyrus may show multiple peaks and with irregular shapes, that which maybe the peak can be different from the symmetric curve or the bell curve, maybe skewed toward one side, or maybe very sharp, or maybe overlapping. So we think the FOF may not be efficient to decompose this kind of spectrum. So the limitation of FOF can be low flexibility in decompose the intracranial EEG spectrum, and also the model, the mixing mechanism, which is multiplicative, which we will refer to it in the following slides. So from this, we were thinking maybe we can do it another way. For example, the non-parametric model. This is a schematic flowchart of our model named CPI. And basically, it consists of 5 steps. For example, this is an instance of the input real power spectrum. And we detect the peaks and valleys, roughly estimate the number of peaks, and we initially fit it. And then we fit the different components into a EM algorithm using the Bayesian approach. So firstly, we will redecompose. It's like a filtering, and we reweight each component, and we will get a new individual component from the real spectrum, and we fit it here with a non-parametric regression. And as we do it iteratively, and finally we judge the fitting by maximizing the vital likelihood, So there are a few features of the proposed CPI model. First one is the individual fit. We only use the monotonicity. This is very soft prior we learned from the data, and the mixing mechanism, linear additive. And the peak number is unlimited. The model can learn from the data, and the loss criteria is maximum likelihood. And here I show the effect of CPI model in a few special cases, considering the shape of the spectrum. The first class may be overlapping, and the second one is skewed, and the third one is sharp. From this result, the first column is CPI, the second is FOF. And if we check the aperiodic and periodic individually, and we can see the comparison here. The obtained evidence in favor of CPI is that the parametric model here, FOF, is not good in fitting the irregular shapes. The irregular shapes here, for example, is the 3 types. And FOF is a multiplicative mix, even enlarge the fit loss measured in the log scale. And CPI as a non-parametric model is flexible in fitting the shape irregularity. Apart from the—
Sorry, Andy, you have 1 minute more. You have 1 minute more, I think.
Oh, Okay, so apart from the special cases, we also evaluated our model using the batch simulation, especially about the centering frequency. We check our model, compare with FOF, we found our model is generally better for FOF than FOF in peak detection. And we also validated the CPI and compare with FOF in sleep staging data, especially caring about the exponent from the AC component. And also the peak discovery, we found the CPI generally better than FOF and is closer to the empirical standard reported by the clinicians. Okay, finally, I think I have no enough time to repeat this summary here, but I want to highlight, emphasize that the CPI can be alternative of FOF to study the scope surface oscillation. But CPI's advantage make it CPI is suitable for quantifying IEG, SEG, even spectral oscillations. We have preprint and codes published online, and we will update the latest preprint and toolbox very soon. Thank you. Thanks for your attention.
Thank you, Andy. Very interesting talk. Let's continue with Yingwan.
Hello everyone, here I will continue discussing frequency domain analysis of the EEG. However, instead of restricting our attention to the spectrum of second-order statistics, I will introduce high-order statistics to determine whether certain EEG components are linear or not. To summarize my presentation in a sentence, the C process is linear and Gaussian, but the algorithm is nonlinear. Brain descriptive parameters describe how our brain functions and how this function relates to clinical variables. For each data, the descriptive parameters are usually obtained in the frequency domain, which reflects obvious rhythm of the brain. The most common DPs are obtained from the EEG spectrum or the second statistics. High-resolution spectrum parameters use the complete spectrum. When we look at the detail of the spectrum, we can see that we can use it as well as described by the components, which are the peaks and the trends. These components are described by the C-alpha model, which has been introduced by Dr. Shang Hu. As he showed, there are two main types of models, C-alpha model and the FOF. C-alpha model considers that the spectrum components are additive in the nature scale, and it's based on the maximum likelihood approach that is advantageous in allowing formal statistic inference. FOF uses the iterative least square to fit peaks in the log scale. The work of C-alpha and FOF patronized the spectra and log spectra respectively of the EEG data to describe the linear property of the components. It gives fingerprints of the brain activities. However, they only capture the linearity of the system. But the brain is a nonlinear system. Nonlinearity are widely studied by neural mass model and other biophysical-based models. So we deemed it necessary to extend the model to the high-order spectrum, at least the bispectrum, allowing us to examine the linearity, Gaussianality, and the existence of harmonic relation among the components of the EEG. Here we use the M9 SEEG data containing 1,772 channels of intracranial recordings to carry study of this nonlinearity. With SEEG, we can minimize the issue caused by the volume conduction. First, we use the bicoherence bootstrap test for the nonlinearity of the EEG. with three specific null hypotheses: linear, linear symmetric, and Gaussian. We can see that the majority of the nodes are nonlinear. We can now turn our attention to see which component, C or alpha, is determining the nonlinearity. So here, we proposed a likelihood-based high-order C alpha model for the joint spectrum by spectrum parameterization for the nonlinearity. In a nonlinear system, according to the Wiener-Vertero expansion, the output can contain integral multiples of the fundamental frequency, and the intermodulation can cause the sum and the difference frequency between the fundamental frequencies and their harmonics. Here is the model formulas and an example of the fitting. We can choose different model for the C and the alpha. The example here, we use the t-student function for the C and the Gaussian kernel for the peaks. With the archaic information criterion, we compare two models, one fitting both the C and the alpha process, another only fitting the alpha components for the bispectrum. The result shows that we don't need to fit the C process for the bispectrum, which means the C process is linear and Gaussian. It also indicates that the nonlinearity are all due to the alpha process. Overall, this is a new version of parametric QEEG with the inclusion of the nonlinearity. We can measure the degree of the nonlinearity of the EEG, especially for each component separately. The next step for us is going to determine what is the relationship between the harmonics, such as whether the amplitude is proportional. We are also needed to link our model to the time domain modeling and include a special organization of components. Thank you.
So now we have the presentation of Anis Lady. Anis Lady, please.
Hello, everyone. I am Anis Lady, and I'm going to introduce an efficient integration of high-dimensional neural mass model with distributed delay. An important tool at this moment in neuroscience is the construction of mesoscopic neural mass model, which describe neural dynamics over time by means of a stochastic or random differential equation. Neural mass models are used to simulate electrical activity of the brain, understanding the architecture of neuron. We follow the classical Janssen and Reed neural mass model formulation, which study the dynamics of three neural masses, two excitatory and one inhibitory. Our new approach in this model is the introduction of a connectivity tensor, including the temporal dimension with arbitrary delay, instead of using a connectivity matrix. Our numerical integration methodology is based on two crucial steps. First, we solve the system of equations with a sufficiently small integration step to ensure that each neural mass gets input from the other masses and can be calculated before solving the neural equation. Neural mass models are very high dimensional, and this approach uncouples the integration of each neural mass with significant simplifications in the solution of the system of differential equations, which is now low dimensional. The second one is finding the inputs for each neural mass. Our differential algebraic formulation creates the present inputs to each neural mass model by an efficient tensor product between the past outputs of all neural mass and the connectome tensor. Traditional methods used in this field to integrate numerically are based on Euler-Maruyama Helm, and Runge-Kutta schemes. Those methods don't preserve the original dynamic of the continuous system, and the standard solution become calculation frequently explosive. A solution to this problem was introduced by Ozaki, employing the local linearization method for the solution of a stochastic or random differential equation. This method guarantees both fidelity and stability, which allow non-explosive discrete time dynamical system, providing a mimic of the original continuous time dynamic system. This is how the discretization of the model, This is how the discretization of the model looks like, where synaptic connections and conduction delays are separated as an algebraic restriction, which helps to numerical integration. These calculations were done symbolically with MATLAB using the symbolic toolbox via a live script. The classical neural mass model was modified to take into consideration conduction delays, linking anatomical connections, considering conduction delays, making the temporal dimension well represented and the simulations more realistic. We implement a brand new type of realistic conduction delays, and for that we explore 3 different delay tensors, given by different conduction velocity. First, we try with instantaneous, then synchronized, and later with distributed delay tensors. As an example, we are now exploring the influence of time delays and connectivities in the thalamocortical system. In this simulation, we analyze the interaction between the cortex, the reticular nucleus, and the thalamus. Here, we are observing the spectral activity of our neural mass model for different combination of delays and thalamocortical connections. To illustrate some properties, let's have a closer look to the display enclosed in the red box. Here, we display the spectrum for 2 different delay values. First, we can see clearly changes among the delays, and they are in accordance with their spectrum. For example, in the case of delay equal 1, we obtain 3 peaks, and we can perceive a slow alpha rhythm, while for delay 9, we have 4 peaks in the spectra, and we obtain the zeta rhythm. We consider that further studies must be done in this area, since new phenomenon could be introduced with variations on delays and connectivities. As conclusion, with the new consideration of delays, the temporal dimension was extended, representing the interactions between neurons through the connectivity tensor via specific connection ways and time delays. The connecton tensor efficiently encodes any realistic delay between neural masses, including distributed delays. We can now model any configuration of connectivities and delays in neural mass model. Numerical calculations are fast and efficient using the algebraic formulation of the local linearization method. And this study analyzed the influence of connectivities and delays into neural mass model, and is extremely important because new phenomena could be introduced. We propose a totally new toolbox for brain modeling that integrates symbolic and numerical analysis to provide new way of introducing delay into neural mass model. That's all. Thank you so much.
Okay, thank you. Let's move on to Carlos Lopez, who will be presenting on mediation and remaining geometry.
Hello, my name is Carlos, and I will be presenting some job about the EEG, about how the EEG cross spectra mediate the effects of early malnutrition or cognition from a Riemannian perspective. So first, I will introduce the problem, and it is that with the emergence of statistical causal theory, mediation analysis is increasingly allows disentangling the relation between genetics, environment, brain function, activity, behavior, and disease. However, when brain structure or function parameters are explored as mediators, these are currently represented as objects lying in an Euclidean space and as scalars or vectors. For EEG functional connectivity, this assumption is not valid. EEG cross spectra are in the Riemannian manifold of a space of symmetric positive definite matrices. So what do? We developed, for the first time to our knowledge, a statistical mediation model for which the mediator is a Riemannian complex valued covariance matrix. For this, we find a simultaneous Euclidean representation of activation and connectivity for PST. We introduce matrix regression based on a nuclear norm for the mediator to analyze the complete frequency spectrum, and we apply this methodology to the EEG cross spectrum. And finally, we demonstrate that both activation and coherence of the EEG spectrum mediate the effect of malnutrition during the first year of life on cognition. So to go back to the basics, classical mediation analysis is limited to vectors of scalar mediators up until now. In this figure, in the left, you can see the basic figure for a mediation analysis, when you have the predictor, the outcome, and the mediator. In the figure in the right, you can see that M has been studied for vectors scalar, but not for when matrix are not for when matrix are a matrix, or when M is a matrix or a Riemannian object. Also, you can apply this method to the cross-spectral mediator. For example, in this case, you have an object that have in the first two dimensions the electrons, and in the third dimension the frequencies. And we can say that there is a mediation effect if the product of alpha times beta is different from 0. And then we can assess that the case when M is a matrix or a Riemannian object has not been studied before, and this is what we do. So why we can't analyze this as an Euclidean space? It is mainly because covariance, correlation, and cross-spectral matrices are PSD and lie in the space of Riemannian manifold rather than in an Euclidean space. Even when these points can be treated as locally Euclidean, ignoring Riemannian structure produces undesirable effects seen in the distance and mean calculations. For example, you can see in this figure that there are 2 points and that the distances, that the Euclidean distance is very different from the Riemannian distance. So therefore, it is necessary to map from the Euclidean to the Riemannian space. And how do we do this? First, we apply the RF reference. Then we apply a regularization method to improve the estimation of poorly conditioned cross-spectral matrices. After we map using the Riemannian geometry theory from the tangent space to the manifold space. And lastly, we apply the vectorization. When we start with a 3D object corresponding to cross-spectral matrices and end up with a 2D object after the vectorization, as can be seen in this figure. So to proceed with the mediation analysis, we want to estimate the coefficients A and B for this model. But the complication here is that in this regression, to estimate the coefficient A, the predictor is a scalar, but the outcome is a matrix. So we use a nuclear norm regularization to find this coefficient. In the case of the B coefficient, the regression is is similar, but it's not the same, because in the outcome you have a scalar, and in the predictor you have a matrix. Also, you apply the nuclear norm regularization, and we can establish that mediation exists if the product of A times B is different from 0. So we carry out a set of simulations to establish, to find the mediation effect. For example, in the first simulation, we blocked completely the indirect effect, and we did not find any mediation effect. For the second simulation, we only blocked one of the parts of the indirect effect, and also didn't find any mediation effect. For the third simulation, we blocked the opposite part of the indirect effect, and once more, we didn't find any mediation effect. And lastly, we only blocked the direct effect, and we leave the indirect effect and the variables to depend on one another. And finally, we found mediation effect, as can be seen in this matrix. So in order to apply this methodology, we study the effect of malnutrition, the study of the effect of malnutrition in the brain. For this, we use the Barbados data, in which for the predictor, we had control and subjects that suffer from malnutrition during the first year of life. We also, for the mediator, we had the EEG that was recorded when subjects were 5 years old, and that this EEG cross spectral is a structure of 3D for each subject, where for the first 2 dimensions are the 19 by 19 matrices corresponding to the EEG channel, and for the third one represents the frequency. And for the outcome, we had a cognitive test. So what did we find? So mainly that both activation and coherence of the EEG spectrum mediate the effect of school-age cognition of malnutrition during the first year of life. This was seen mainly in the alpha band connection in the scale between the mediators, between the malnutrition effect and cognition. And you can see that the alpha band is the most prominent, showing 5 long connections. So to conclude, statistical mediation model for which the mediator is a positive semi-definite matrix is possible and effective. Matrix regression based on a nuclear norm for the mediator allows analysis of the complete cross-spectrum frequency. Third, it is possible to develop an efficient method to carry out this methodology. And lastly, both activation and coherence of the EEG cross-spectrum mediate the effect of malnutrition during the first year of life on cognition. Thank you so much.
Thank you, Carlos.
Okay, thank you. We can continue with Ronaldo.
Hello, guys. My name is Ronaldo Cesar Garcia Reyes. I am a mathematician from the Cuban Neuroscience Center, and I work on the supervision of Professor Pedro Antonio Valdez Sosa. The name of my presentation is Multivariate Intrinsic Local Polynomial Regression, Isometric Riemannian Manifolds, and its application to post-indefinite data. This work is a collaboration between the San Euro Institute and the USTC University. So first, I want to point out that this work is a generalization, is a continuation of previous work performed by the GBC in the harmonizing multinational QEEG norms. In particular, we propose an upgrade on some of the features on the pipeline in this paper, in the regression models and the Aulari detection models. This paper proposed a new intrinsic non-parametric regression method using isometric Riemannian manifolds, which has potential application in machine learning and neuroscience applications. Specifically, the symmetric positive definite manifold, a mathematical structure that arises in machine learning and neuroscience application, is considered. We derived the closed analytical expression of the intrinsic local polynomial regression on the SPD manifold for the Euclidean pullback metrics. and we prove the consistency of the estimator for the complete family. In particular, we show that the Log-Cholesky metric have better performance than the affine variants with respect the accuracy and the computational time. We also implement a geometry-aware Riemannian TNSNE method for visualizing high-dimensional SPD data. So, positive definite data arise from different sources in neuroscience in the form of cross-spectral tensor, diffusion tensor, correlation matrices. This positive definite data is a nonlinear type data that is more accurately modeled with manifold and Riemannian manifold. The real case of positive definite matrix manifold is known as the symmetric positive definite manifold, which is a manifold, and a manifold is a topological space.
Do you have
How I was saying, positive definite data arise from different sources. This is a non-linear type of data and is more accurately modeled with manifolds. A manifold is a topological space that locally resembles a Euclidean space, and when they keep a manifold with a metric tensor in the tangent space, you get a Riemannian manifold. So some applications of Riemannian regression methods in neuroscience are noise removal, data harmonization, and feature modeling. So mathematicians have the tendency to take a problem and generalize it into a more abstract settings and then solve the original problem as a particular case. So Riemannian regression methods can be classified according to the extrinsic and the intrinsic approach. Both approaches can be classified according to the non-parametric and the parametric cases. The work done performed in the harmonic QEG papers correspond to the Riemannian regression extrinsic methods, and the proposed method during this research correspond to the intrinsic Riemannian regression methods in the non-parametric case in the local polynomial regression method. So a typical intrinsic local polynomial regression problem looks like this, and as we can see, depends of the internal Riemannian operation, have the Riemannian distance and the exponential map. When ignoring the geometrical structure, you get the local polynomial regression problem in the Euclidean space. So this table shows some of the main difference between the extrinsic and intrinsic approach. And the conclusion is that the intrinsic Riemannian regression methods are in general more accurate, but require more computational time. So in this first picture, we can see the different Riemannian regression methods. In the first row, we get the extrinsic approach. In the second row, the intrinsic approach. And in the last row, we can see the intrinsic Riemannian regression method combined with isometric Riemannian manifolds. So the general idea is to get a data with responses in a manifold and mapping this data into a new manifold with a more straightforward geometrical structure that allows to solve more easy the intrinsic local polynomial regression problems. And the idea is based in isometric Riemannian manifold, which are Riemannian manifold that share similar geometrical characteristics to an isometry. This isometry allows to connect all the Riemannian operations between the two manifolds. Therefore, we can connect the intrinsic local polynomial regression problems in the two manifolds. So other important concept during this presentation will be the Euclidean pulbar metric concept. These are Riemannian metrics that arrive from pulling back the Euclidean pulbar metric. So the main theoretical results is that when you have two isometric Riemannian manifolds, the intrinsic local polynomial estimator are connected by the simple closed analytical expression. And when the original Riemannian manifold is equipped with the Euclidean pulbar metric, the intrinsic local polynomial estimator have a closed analytical expression that resembles local polynomial regression in the Euclidean space. So other important theoretical property is the asymptotic bias formula for the estimator, which implies the consistency of the estimator and also the pseudocode to implement this estimator in any language, any program language. So As a particular application, we have the application to the symmetric positive defining manifolds. Some of the main metrics in the symmetric positive defining manifold are the Euclidean, Euclidean, low Euclidean, Cholesky, log Cholesky, and the affine variant metric. We show during the in our research that some of these main metrics to explore the symmetric positive defining manifold are in fact Euclidean purbar metrics. This allows to us to solve the intrinsic local polynomial estimator for these metrics. And the performance of this metric with respect to the established extrinsic local polynomial regression using a affine variant is compared using Monte Carlo simulations. This is the model to generate true data for a specific dimension of the covariable and manifold dimension. This is the model for add noise to that true data, and the score to measure the error is the root mean square error. So in the case of the symmetric positive defining manifold with dimension 3 correspond to the DDI simulated data. In this case, we have the first row is the true data, the second row is the data contaminated with noise, and the following rows are the estimated data for different methods, the low-Cholesky method, the low-Euclidean method, and the established extrinsic local linear affine variant. The results is that low-Euclidean method have best performance in the case of DDI simulated data. So in the case of high dimensional, what we do is that we want to know how this performance scale when you change the dimension of the covariables and the dimension of the manifold. So each of the dots of the first picture correspond to a specific covariable dimension and a specific manifold dimension. What we see in this picture is the log-Cholesky metric have the better performance when scaling the dimension of the covariables and the manifold dimension. And the second picture, we can see the result of performance Riemannian TNSN compared with linearized PCA in the tangent space. What we can see is that the Riemannian TNSN is more capable to capture the nonlinearity of the data respect to the linearized PCA. So some of the conclusion, these are some of the conclusions of the paper. I cannot see well. Moment. So the definition of the multivariate intrinsic polynomial regression is generalized to handle responses on an arbitrary Riemannian manifold. The exact analytical expression of the multivariate intrinsic local polynomial regression on arbitrary Riemannian manifold given with the Euclidean purbar metric is derived, and we prove also the consistency for the complete family. We prove the Cholesky metric is also the Euclidean purbar metric, and we perform as in particular, we derived the analytical expression of the intrinsic local polynomial regression on the symmetric positive defining manifold equipped with an arbitrary Euclidean purbar metric, and we make a study of the performance of the estimator for different metrics, and we conclude that the log-Cholesky metric have the better performance, and we implement Riemannian TNSN for visualizing data on the SPD manifold. All the codes for implementing the intrinsic local polynomial estimator and the Riemannian TNSN and all the relevant calculation is available in the GitHub page. So this is some of the main reference, and that is all, guys. Thanks for your time.
Thank you, Ronaldo. Great presentation. Now we could have some minutes for few questions. Okay, Carlos, do you wanna ask something?
Yes, I would like to ask about the first presentation to Ludovico. Is Ludovico around?
Yes, I am. Thank you.
Oh, yes, very interesting presentation. And
Thank you, Carlos.
yes, from where I see, from where I saw, you did, let's say, a lot of signal generation, but all that I saw was from the analog perspective, just using analog circuits. I was wondering to myself if it is possible or even better to use, let's say, some digital processor like some FPGA or DSP or something like that, if you have considered those options to generate those kind of signals. Thank you.
Beautiful question, Carlos. Thank you for asking me. Now, this is a deep question that comes up over and over. Also in terms of many papers that I get to handle as an editor. And there seems to be a little bit of confusion in the literature about this. Now, the situation is this. When we use a digital circuit to perform a numerical calculation, such as the integration of an equation system, there is no conceptual difference with respect to running it, say, on MATLAB. So all the works that use FPGAs, for example, or use DSPs, from a theoretical viewpoint, that's just numerical computation. So there is theoretically no merit in doing that as compared to running it on MATLAB. Now, that's not to say it is not interesting. It's very interesting from an implementation viewpoint. But the thing that I, as a physicist in this case, I am interested in is the fact that a physical, as opposed to a numerical nonlinear system, has a lot of nuances, has a lot of interesting properties that otherwise we miss. These are due to non-idealities, to complex mismatches, and they are also due to aspects that are inherently down to its physical nature. For instance, stiffness can be a very serious problem for solving some large equation systems. So the short answer to your question is, if we use digital to do computation, well, it is, as I have said. There remains the possibility of using digital circuits to do asynchronous networks, which is a completely different thing. So not integrating an equation system, but that's an area that I have not explored because I'm also quite interested in continuous dynamics. So it's not something.
Okay, thank you so much.
Okay, is there another question? Does anyone else want to make any question?
Yes, Annie, I have one question for Lodovico.
Okay. Yes.
Professor, I see that you talk about phase synchronization, right? No?
That's right.
I made some work in neural fields related to the Kuramoto models. You are aware of this theory?
Of course I am.
Yes, I see. I see a lot of your results made me recall the Kuramoto model and phase transition in these cases. So I want to make the question: what is exactly what you do respect this team?
Okay, beautiful question. You have to be very careful and consider a few things. So first of all, let us consider only equation systems. Okay. Now there are two types of systems. There are phase oscillators, where the only free variable is the instantaneous phase. And there are oscillators that have free phase and amplitude, such as the Stewart and Dow systems. Now, the beauty of the Kuramoto model, as you know, is that under certain conditions, it allows to some extent some analytical tractation, some analytical solution, which is very beautiful. But as a matter of fact, the vast majority or near totality of natural dynamics also involve free amplitude. Now, this means that you have systems that when you couple them in a network, they exhibit behaviors that are potentially much more complex than those accessible to the Kuramoto model. Now, that is not to say that you cannot calculate phase synchronization. You absolutely can. because what you do is you use things such as the analytic signal to get the instantaneous phase, and then you can calculate phase synchronization very easily. So in the case of the Kuramoto model, phase synchronization is everything that you have. In the case of these systems with a free amplitude, it's one of the aspects, but you can calculate it fairly easily. Okay, then in my case, there is the physical aspect. So the fact that I realize such systems, not numerically, but physically. Now, as I explained before, the interest in doing that is from different angles. So in general, there is the fact that when you create large networks, the kind of mismatches and non-idealities that you get give you a lot more behaviors than you can get in a simple stylized numerical model. So they are different ends of one spectrum. The Kuramoto model is timeless and incredibly influential because it is so fundamental, and it gives you as a price the fact that you can treat it analytically. But it is a very, very abstract view of reality. I am at the opposite extreme.
Yes, I know. I see that in some publication that when you generalize the Kuramoto model in neural field, you get this chimeral state that you was talking about.
Yes. Do you know also what is very important?
They call this type of model next generation neuronal field models. Yes. And there arise the chimeral state and the alpha beta rebound and all these type of synchronization phenomenon.
And the key thing there is...
It was a very interesting presentation.
Yeah, I'm not very familiar, but I know what you're talking about. Do you know what makes the key difference there? The presence of delays. So in the origin, that is the point. That makes a huge difference.
Exactly.
Because in the initial Kuramoto model, there are no delays. The presence of delays...
There are no delays.
This is the point. When you have delays, you have effectively infinite dimensional dynamics that are possible. So all sorts of things can emerge. However, unfortunately, you lose the initial ability to have analytical results, because you save the Kuramoto model, but the fact that you put a delay kills that possibility.
You don't have the exact analytical expression, but you can get some general results. For example, in neural field, you cannot have the exact solution for the spiking rate or the potential in some point, but you can get the relationship between the synchronization state and the thermodynamic state of the system. That is something really interesting. You can get the relationship between the synchronization, Kuramoto parameter, and also the spiking rate. That is a very interesting if we can prove this in an artificial system. Will be an interesting investigation if we can simulate the relationship between the Kuramoto parameter and the thermodynamic state of simulated spiking neurons. That is just one idea.
Oh, it's a very good point, and I hope we can continue the discussion further. I just want to mention one thing. You are deeply correct that the relationship between synchronization and thermodynamic aspects is extremely important and extremely interesting. There is one other situation that I find very inspiring and not very well studied, and that I am studying presently. Systems that have free amplitude, but that are conservative. Because this is one interesting aspect. So the vast majority of chaotic oscillators are dissipative, right? But not all of them. So the question of what it means from a thermodynamic viewpoint, the establishment and maintenance of synchronization in networks of purely phase oscillators, which are conservative by construction, chaotic oscillators that have free amplitude that are dissipative on the other extreme, and in the middle, this middle ground where you have systems that are with free amplitude but are conservative. This is another area that is it's kind of related to what you said, and I'm just now actually starting to work on it a little.
Well, we can collaborate in this theme
Okay.
whenever you.
Thank you, guys. Very nice discussion. And now we could move to the main room for final summary of the Global Brain Consortium. Thank you.